So let me do this question. This is, I think, I think this is the only question in the set I'm doing today that's not from the end of the textbook. Or it's not from the end of the question set. It's question 55. I think there are other questions that's similar. I think I've done question 54 before. So in any case, let me do this question. It's talking about a cyclotron, and I think a cyclotron is covered in the textbook. So what you have to imagine is you have to imagine a setup that has kind of uniform magnetic field set up in a region. I'm just drawing like two. I don't know. I'm just doodling, sketching to make sure I understand the setup. So imagine this is like a north pole of magnet. This is south pole of magnet. So within this region, you have a uniform magnetic field setup. And when you have a uniform magnetic field setup, if you have a particle in here, for example, that's let's say moving in this direction, then the kind of the magnetic field force that will be on that particle, let's see, V cross, assuming it's positively charged, V cross B will give you a magnetic field pointing out of the screen. Oops, so I think I drew it kind of wrong. For particle moving in that direction, I should really have it going like on the back side there, so that as it's going that way, so okay, V cross B, let me double check it from my perspective. There's gonna be kind of like a centripetal force that's pulling it towards inlet. So this particle will end up tracing a kind of a circular path as it's moving, and there will be a centripetal force pointing towards the center of the circle as this particle is moving. So it's giving me some information about the maximum orbital radius of the circulating protons. So let's just label it this way. Let's say the edge is where you're going to have that maximum radius. Let me call that R max. So it's asking what is the kinetic energy of the protons when they are ejected from the cyclotron. And reading this, unless you've read about the cyclotrons in the textbook, you might be wondering, kinetic energy, it's not like voltage difference accelerating the charged particle through that electric potential difference. What does kinetic energy have anything to do with it here? So here you have to do a kind of a force analysis. This is really why in the earlier in the semester in the mechanics review I included the circular motion problems. That's because in a scenario like this, really what you have to analyze. Let me draw the top view so that it looks a little bit better. So from the top view, what I basically have is the circulating proton. Let's say it's at R max, radius R max, and when it's over here moving at some speed v, then the reason it's moving in circles is because there's a centripetal force on it. Call this Fc, and this centripetal force from the circular motion kinematics, you can say this is equal to mass times the centripetal acceleration, tangential speed v squared over r. And in analyzing this setup, you come to a conclusion or know somehow that the only force that's providing this centripetal force is the magnetic force, which if you are looking at the magnitude of the magnetic force, that's given by Q V cross B. So this is the kind of the piece of physics that you have to know in order to answer the question, the kinetic energy, which will be related to V squared. So I think I have most of the things I need here. Let me do this. I'm gonna try to construct an expression that's going to look like kinetic energy of the particles, which will be 1/2 mv squared. I already have mv squared here, so I like that. I think I can basically multiply both sides by r and then divide by 2 to get something that looks like kinetic energy. And the arrangement here makes things simple because the velocity, the way you have it set up in a cyclotron, it's going to be perpendicular to the magnetic field. So I can just say the magnitude of the V cross B is simply VB. I don't have to worry about that sine theta that comes from the cross product. So let me just do this quick bit of algebra. Doing that gets me, gonna say kinetic energy is equal to 1/2 mv squared, which comes from this term, multiply by r to get rid of r in the denominator, divide by 2 to get 1/2, and I write down the right hand side, which is gonna be the amount of charge, VB. Now I do this times r divided by 2. And I think all the numbers here, oh wait, yeah, I shouldn't have done it that way, sorry, that was my bad. Yeah, so this is one of the kind of downside of trying to take a shortcut and not being systematic. Like my advice to students is usually be systematic. In trying to take a shortcut, I forgot that will have V on both sides. V is not one of my knowns. So let me just scratch all this out. Really the thing I should do is take this expression here, don't do this, just solve for V. So let me just write down the simplified expression, or clean expression, mv squared over r is equal to qvb. Now I can simply solve for v. Cancel out v here. So solving for v, so I'm gonna move m and r over to the other side. It's gonna be r times qb divided by the mass of the particle. Now I can use this to properly build my kinetic energy expression. Kinetic energy is equal to 1/2 now mv squared. So I'll have 1/2 m and then this thing squared. 1/2 m times r squared q squared b squared divided by m squared. And now if I want, I can cancel out a factor of m. But you know what, let me not bother with that and just plug in all the numbers I have. So I have the mass of the proton, I have the maximum radius, I have the charge of the proton, the elementary charge, I have the value of the magnetic field. So I can just plug all those in. Let me do that in Wolfram alpha, this expression here, and I'll go that way. Yeah, sorry, I should have been careful from the beginning, not try to take shortcuts like this. Yeah, okay, so let me put it in. I'm gonna just put in all the units that'll actually help me do part B pretty easily. So I'm gonna say kinetic energy is 1/2 times the proton mass, 1.673 E minus 27 kilogram. I could also type proton mass and it'll look up the right mass, but let me do it this way this time. Oh wait, 3 typo. Mass times radius 0.421 meter meter squared. And once I decide to put in the units, then I have to do it for all the quantities I can pick and choose. Times the charge. Here I could say elementary charge, and it'll get the right charge. And when you specify things this way, it automatically includes the units. It's part of the physical quantity. The magnetic field 0.985 Tesla squared. All of that divided by this amount of mass, proton mass, squared. I probably could have saved a little bit of work by combining this and squaring them all together. But it's fine. So this should give me kinetic energy of protons, and it'll give me the number in a couple different units. It's possible. Wait, were there missing? Oh yeah, I think I forgot to close that parenthesis here. I think that's where I was gonna close it. So it might give me answers in joules and mega electron volts without me specifying. So all of this looks right. I got joules, 1.32 times 10 to the minus 12 joules. It worries me a little bit that it has so little significant figures, but I think it'll be still within 1% tolerance of the system, grading system. And then there might be, yeah, there it is, mega electron volts, 8.23 mega MeV, mega electron volts, 8.23. So let's make sure that's correct. Good. So Parsi asks, through what potential difference would a proton have to be accelerated to acquire this kinetic energy? And this is the kind of the advantage of cyclotron. You can have it gather this much energy kind of over many cycles of circulation. Here it's now asking what if it was a linear accelerator? You are accelerating one shot through a single step of voltage. Well, what does that look like? So I think let me just sketch out the analytical expression I need, and I'm gonna use the calculation that I've been doing. So the amount of kinetic energy I have, it's gonna be so in the setup of part C, that should be related to the potential energy difference that you would set up. So potential energy, and that will be related to electric potential specified in volts. So this should be amount of charge times the amount of volts. So solving this for voltage or electric potential, that should be the amount of energy you have divided by the amount of charge. So I think all I have to do is really take the expression here and divide by one factor of elementary charge, which charge of proton, which I can do by just getting rid of this square. I think that accomplishes what I'm looking for. So let's do that and see if that's right. Let me actually snap this top so I don't. Okay, it did a calculation. There should be an answer in volts. There it is. Yeah, pretty large. 8 million volts and 230,000. 8.23 E6 volts. And I guess that's achievable in a that's not too far. I think there are Van de Graaff generators that charge up to like millions of volts. So that might be achievable, but that's a really high voltage system. Whereas this is almost like I think it's almost a tabletop geometry. Half a meter. You could build this and put it on a tabletop. What is the period of the voltage source used to accelerate the protons? Don't let the whole voltage source confuse you. All it's asking for is a period of the cyclotron thing. So normally I think in your textbook there's a picture of a D-shaped thing, and there's a gap. In the gap, you accelerate it in the right direction each time as it goes around. So the period that it's really asking for, it's asking for the cyclotron period. So I'm gonna calculate how much time does it take for the proton to make one full circle turn, and that should be the period. And I guess it might also be half a turn, maybe. Let me try with one full cycle, and then let's see if that works. Let's see. I think I can erase these abortive attempts from earlier and have space there. I might have needed to do this on OneNote instead of doing it on this limited screen space. So I'm thinking of period. That's the duration of time. And the way I remember things is, speed is distance per time. So solving this for time, I get period should be distance, which is going to be the circumference, divided by speed, which ought to be this v that I already worked out. So, so it should be distance, the circumference, should be 2 pi r, and the speed will be this v that I worked out. And I think once I have this much written out, then the rest I can just do it in Wolfram alpha. I'm gonna go back to this expression, kind of isolate what was my v. So it should be, let's say here, r, just one factor of r, times q, times b, divided by mass. That's my v. Okay, just kind of have that as one thing. I'm gonna be putting that in the denominator, and I need to multiply by 2 times pi times r. 0.421 meter. Now there are, simplifications I could have done. I think your textbook actually has a cyclotron frequency. I could have looked that up and take the reciprocal. Here I'm just doing things from scratch. So this should give me some time. Wow, nanoseconds. Okay, that's comforting that the question is expecting answer in the units I already have. So 66.61 nanosecond. Let's hope that's right. If that's not right, then I'm gonna try like a half of it maybe. Okay, that's right. Yeah. All right, repeat the calculations for alpha particles. Oh, I probably should have done this alongside. Let me go kind of backward because I already have this expression. All I need to do for alpha particle is I need to change the mass. So alpha particle mass is same power of 10, but this should be 6.645. It's probably close to 4 times what I had before. So that should give me the last answer for alpha particle. Pretty large. Oh, right. I think a heavier particles, I don't know if I think they do, wait. Oh, why does it say that's wrong? Let me just make sure I plug in the numbers right. 6.645 times 10 to the minus 27. It's possible there's a rounding issue. Oh, an elementary charge, right? Alpha particle has twice, double the charge. So, okay, 2 times elementary charge. That's going too quickly. So that should be 132.3. 132.3 nanoseconds. So let me go back and now do the rest. I think it's actually better to get the kinetic energy first. So let me go back to my expression for V. That's the expression for V. And I'm going to square the whole thing just together this time. And then times the 1/2 times the mass. Alpha particle mass was this. So that should give me kinetic energy, and that'll give me answers for the first 2 parts, I think, kind of at the same time. 1.33 E minus 12 joules. I have no sense of scale for joules. Is the kinetic energy? It's the same. Or more or less the same, I guess it must be because, so it has a larger charge that makes it, so I think I don't know. This is the kind of the number sense that I don't have a good intuition for because it's not a situation that I encounter all that commonly. So, but I think those are right. Let me just double check to be sure. So I got those kinetic energies, good. Now potential difference. So this entire thing is the expression for the kinetic energy. I'm gonna divide by the amount of alpha particle charge, which is 2 times elementary charge. So that should give me the voltage 4.1. Yeah, so the voltage is different. I don't know. Wait, 4.15 E6 volts. It's a quite practical, quite common setup that uses magnetism in a practical way for particle physics, but it's not my area of expertise, so I don't have an immediate intuition for when you double the mass, quadruple the mass and double the charge, how should these quantities change? I don't have an intuition for it. I think if I simplified these expressions, it might give me something, but I was too lazy to do that.